My name is Mick North. I'm the CEO President of Anderson Global. Today I'm sitting here with Pavel and Ben, and we're going through a recent cooling study that we conducted for an automotive customer that was looking to take cycle time out of their process because they were running up against capacity constraints. This is the more detailed presentation that will take you through the exact methodology that we used. So, Pavel, go ahead.
Thanks, Mike. What you see on the screen is a complete mold assembly that the cooling study was done on. You can see it's a fairly complicated assembly with a bunch of moving parts, 4 slides, and pour basin. So we were building tool set number 3, and the customer asked us if we could improve their cycle time. Here is the general information that was provided, what we used for initial base analysis. Here's the general layout of the mold: exhaust slide, front slide, intake, and rear slide.
So that's looking from above, correct?
It's looking from above.
Yeah.
It's a cylinder head casting for a high performance engine, 3-cylinder engine. And on this slide, what you see is the current cooling that the customer is running, and they're getting about 11 parts an hour of this cooling, and they ask us to improve that to about 15 parts an hour. So we did a bunch of analyzing of the tooling, as there was already existing features in the cooling, which we had some leverage to change as it was a brand new build, but the process was proved and it worked, so there were some limitations there.
So the trick here is to add enough cooling to raise increase the solidification rate to go from the 11 to the 15. And that's what you basically do in your analysis.
Yep, we just want to extract as much of thermal energy as possible in the shortest amount of time. More cooling, the better. However, you have to be careful to not change the solidification pattern. So we had a cooling line in each slide, and also a combustion insert spiral cooling on each.
Yeah. Let's just talk a little bit about that. Ben, maybe you want to just give like 10 or 15 seconds on that combustion chamber and tell everybody that there's going to be more information coming on that, right?
Yeah, with the combustion chambers, it's always been a traditional, cross-drilled hole, comes up from the bottom. We have one that comes in from the side. It required us to weld and plug up the holes. So during the analysis, we were challenged to try to eliminate that and make a more robust tool. And with that, we were able to come up with a design of a plug that fits up through the middle, and with the combination of a special gasket and certain amounts of pressure to bolt on another plate, we were able to come up with a conformal cooling to help these combustion chambers cool even faster.
Right, because typically that's a hot spot in the tool, isn't it?
Combustion chambers is a very important one to make sure that the metal properties are met at that very specific point, because there's a lot of pressure from obviously with the engine and everything like that. So
yeah, we were just talking as a group here. We're gonna do a separate video on just that subject there, because there was a lot of analysis and testing that went into that combustion chamber cooling circuit design. We'll cover that in a separate video. Please continue, Pavel.
What you see on the screen is the information that we used for calculating the heat transfer coefficients, which is what gets plugged into a simulation software. Along with that, we have a capability of describing the cycle in very detail. So whatever the process, manufacturing process is, we have capability of basically just plugging into our software and mimicking what's happening on the floor. You can see here on the screen just basically the cooling and the heating of the mold, all the segments of different in the manufacturing process, ejection, anything. So we used a couple calculators to make sure that we are getting a turbulent flow in our cooling lines, which is what we want. Turbulent flow is desired versus the laminar flow because it extracts more heat. It extracts more heat from the mold with thermal energy. So we have a couple calculators that we make sure that what we design is right.
So the higher the Reynolds number, the more turbulent the flow. Am I correct?
Sure. And the Reynolds number and the heat transfer coefficient, the calculator is basically the function of the diameter of the cooling line, the flow rate, and the temperature of the media that you're using to cool with, which is normally water.
Okay.
There was some constraint from the customer. They had the closed cooling system in their foundry, meaning they had a big tank elevated, so they weren't using the typical water pressure from the city. So we're able to plug that in and make sure it'll work.
So pressure was fixed. So really, you're working with the variables around the diameter of the pipes and the lengths.
Yep. And here you can see on the screen we have another calculator that we can calculations, and come up with that heat transfer number. So that just kind of shows you the cooling line in the slide, and of course the cooling line had to be designed in a manner that's manufacturable. Drilling deep holes is usually not the easiest thing. It's expensive. We're showing the cooling line and the base insert. So in addition to the combustion chamber cooling, the spiral cooling, we had the cooling line and the base insert to keep the steady temperature.
You just raised a good point there, which I think is important for our customers to hear, is that the two of you, in fact, all of our engineering department has strong manufacturing knowledge. All of you have worked in manufacturing for many years, so you're not just designing stuff that meets the calculation, but you're actually designing stuff that can actually be made in practice on the shop floor, which is pretty critical, I think.
Sure, it's very critical in the foundry business. It's generally pretty rough environment, so we want to make things as simple as possible. The saying is simpler the better, but it has to work, has to perform. What you see here on the screen is just a comparison of the two setups. On the left, you see the current cooling setup. The customer was getting about 11 parts an hour with that setup. On the right, you can see all the additional cooling lines that we added in each slide and the base insert and the spiral cooling. And with that added, we were able to get 15 parts an hour, which is a significant improvement.
Yeah, so I guess what I'm looking at there is I'm looking at similar points of solidification, but the one on the right has happened significantly quicker than the one on the left, hence the 15 parts an hour.
Yeah, so we shaved off about 60 seconds roughly. So pretty significant for
yeah.
Here, what you see is just an animation of the solidification cycle. And why we did that is we were not necessarily responsible for a solidification pattern, as it was existing tooling, proven, it worked. However, we wanted to assure that we didn't change our additional cooling. The intent was to reduce the cycle time, but so that was a double check. We ran the full analysis and it worked well. Next slide is showing the temperature of the casting at 220 seconds into the cycle. And that is the current setup without additional cooling. And here's the setup with added cooling lines. And you can see a significant difference, especially at the bottom of the casting, where it's much cooler at the same point in time in the cycle.
This is looking at temperature. So the light blue is the 400 degrees. So at the same time, we've got 400 degrees, much broader spread of it at the bottom of the component. Yeah.
Yep. We also add additional cooling into the riser. The top section of this is a large riser feeding it, so it solidifies from bottom towards the top. And this was obviously staying liquid for the longest. We did have a cooler that shot at the kind of open air to speed that as well. So here you're showing it's a cross-sectional area of both setups. Again, showing that the added cooling made a significant difference, and it dropped the temperature in the combustion chamber area, not only in the combustion chamber area, in the whole setup. Here's another section. You can see the spiral cooling at the bottom. So when you look at the scale, you see how much hotter the center of this combustion chamber area is. You're seeing yellow and dropping the temperature here into red.
Yeah.
And that's how we're able to shave off those 60 seconds. But structurally did not change the casting.
Yeah. How many iterations of different cooling designs do you think you went through approximately?
We had roughly half a dozen different types, I would say, and total of 11 iterations.
Yeah. Okay.
Particularly challenging, out of the ordinary with a specific design, Pavel?
The challenge was to fit the cooling lines around the mold. So you see, I mean, you got long drilled holes, and when I show you the very first one, there's a lot going on. Bolts going through, and those are standard components the customer did not want to change, right? I mean, they don't want to change the bushing size and the location of even the mount hole, because that's interchangeable with the previous tooling. So that was pretty challenging to make sure that we can fit all these lines and they can be manufactured.
Thank you.
We solved the problem.
Thanks, Pavel. If you want to know more, there's more videos on our website, and you can take a full look at our capabilities over there.